Hello everyone, my name is Kelly Hao and I am an upcoming assistant professor from Georgia Tech. Today it's my great honor to introduce our work, 3U-EdgeAI, ultra-low memory training, ultra-low bitwidth quantization, and ultra-low latency acceleration, which are three key enablers for AI on the edge. This is a collaborative work among different institutions, including ADSC in Singapore, UC Santa Barbara, and Georgia Tech. First, I think all our audience are quite familiar with the concept of edge computing, and we know that the edge devices are power limited, resource limited, memory limited, and in most cases, we still require real-time response. This makes edge AI really challenging. And this is the typical design flow for edge AI. In each step, there are numerous challenges and research interests, and none of them is trivial. So in this work, we will cover these three major steps. First, we will talk about training. So we propose an ultra-low memory method for on-device training. The second is quantization. We propose an ultra-low bitwidth quantization for resource and memory saving. And the third is based on the quantized machine learning model. We propose a low latency accelerator for real-time response. So this is the first work, On-FPGA rank adaptive training using ultra-low memory. So this work is collaborated with Cong and Kaiqi from UCSB. Training on the edge recently has been attracting a lot of research interests for privacy and security concern. It is also very challenging that it has a large memory requirement, including the model weights, activations, training samples, and gradients. There is a promising technique called low-rank tensor decomposition that can largely reduce the model size. So, based on the promising low-rank tensor decomposition and challenged by the large memory requirement, our work aims to propose an efficient on-device one-shot tensorized training. So there are two primary contributions. First is, instead of using a fixed rank for tensor decomposition, we propose a rank adaptive training. This can avoid complicated search of tensor ranks and multiple training runs. And the second contribution is we propose the first FPGA accelerator for on-device training. So here are some background knowledge. What is tensor decomposition? This is the original tensor. In this case, this tensor is order 3. This is the CP decomposition that each term can be represented using 3 vectors, and we just need to sum them up. This figure is an example of Tucker vectorization, that the tensor in the middle here is much smaller than the original one. This last one is called tensor train vectorization, or also tensor train matrix format, that the original tensor can be decomposed into 2 vectors and several matrices. So in fact, tensor decomposition is exploiting the low rank feature of the original tensor, and the new representation requires much fewer parameters, from an exponential function of d to a linear one. And also this tensor decomposition can be applied to fully connected layers, convolution layers, and embedding tables. But this is not an easy task, absolutely non-trivial. And why is that? Because determining the rank during the deep neural network training is very challenging. So first, determining the rank itself in advance is already very hard, and it is further complicated by the nonlinear forward computation in neural networks. But we want to solve it. We want to determine the rank during training. So the key idea we use is we use Gaussian priors to model the low-rank tensor factors, and then we can introduce some rank controlling hyperparameters during training. And then we co-optimize the rank controlling hyperparameters together with the model weights. So in this way, we can determine the rank during training, which is called rank adaptive. To skip the technical details, but to briefly summarize, we developed several basic models. The first is a stem variational inference, and the second is the stochastic variational inference. And in this table, it shows part of the results. We can see that using this rank adaptive training, we can achieve a remarkable compression ratio that is more than 26,000 times. This large compression ratio actually enabled our next work, which is on-FPGA adaptive training. So thanks to the tensorized training, all the parameters can be stored on chip now. So in this figure shows our overall architecture for FPGA-based rank adaptive training. So there are different processing elements to compute different functionalities here, like P1, P2, and P3, and we store all the model weights in VRAM. Our initial prototype of the FPGA accelerator is on an Ultra 96 FPGA, which achieves 59 times faster and more than 100 times more energy efficient than an embedded CPU Raspberry Pi. Of course, this is still an initial work on the Fashion MNIST dataset, but we can already see that the memory reduction is already more than 200 times. We believe that using rank adaptive tensorized training can be very promising for on-device training. After the on-device training, let's take a look at the quantization. Here we proposed an ultra-low bitwidth quantization with vectorized loss. We call it VecQ. This is a collaborative work between Dr. Chen from Singapore ADSC and myself. I think most of us are familiar with quantization. The primary task about low bitwidth quantization is we want to find two sets of variables, fixed representations and scaling factors. So here, this omega f represents the original floating point weight, and we want to find is this quantized omega q that is represented by the scaling factor alpha times this vector of fixed representation, alpha and v. So in most traditional quantization approaches, they use L2 loss that try to minimize the L2 distance between the floating weights and the quantized weights. But what's wrong with it? First, minimizing this L2 loss is non-convex and it's hard to directly optimize and requires an iterative approach. And also it neglects the weight distribution. For example, in our observation, in most layers, the weight distribution is Gaussian-like. So instead, our approach is we are no longer using this traditional L2 loss, but proposed our own vectorized loss. We call it VecQ. So what does this vectorized loss mean? We already know that we can organize all the weights as a vector. For example, this omega f for floating point weights is a vector, and this omega q for quantized weights is also a vector. The left figure is an illustration of the two vectors, assuming there are only two elements. So we define the vectorized loss, denoted by JV, as a summation of two losses. The first is orientation loss, JO, and the second is modulus loss, JM. First, for the orientation loss, we want to compute the angle between the two vectors, here, theta. In this stage, we only need to care about this unit vector of the fixed representation, V, and we want to minimize this angle, theta. The second is modulus loss, which is the original L2 loss between this omega q after scaling and the original floating point vector. So the vector loss is the summation of the two. And the advantage of using this vector loss is that we can have a better chance of getting lower quantization loss than L2. So the next question is, how can we minimize this vector loss? Let's recall that our objective is to minimize this GV equals JO plus JM. And we want to find the quantized values, which can be represented as a scaling factor alpha times the unit vector of V. So it can be done in two stages. First, to minimize the orientation loss JO, which means we're trying to find the best V by turning this V around omega f and find the smallest theta. We call it steering stage. And in the second stage, we minimize the modulus loss JM by finding the optimum alpha. We call it driving stage. So these two stages can be done independently, that we can optimize the first and then optimize the second. More details can be found in our original paper, but now let's jump to the effectiveness evaluation. From this table, we're only showing the low bitwidth results from 1 bit to 4 bits. We can see that comparing with all the existing low bit quantization methods, VecQ is outperforming almost all of them. So it is really promising. And also VecQ is open sourced and integrated into TensorFlow and PyTorch, and the link can be found here. So after the low bitwidth quantization, we still need a corresponding low latency accelerator that can take the quantized inputs. The next work is exactly doing this, an ultra-low latency Turnerized DNN accelerator. Here we are using ternary weights because it is really memory efficient, but does not lose a lot of accuracy. This is an instruction-based Turnerized accelerator, and it can be used together with VecQ by taking the Turnerized quantization as inputs. This accelerator is also open source with synthesizable Verilog code for embedded FPGAs. In the following, let me introduce 3 secrets to achieving ultra-low latency. Well, the first is an expressive single instruction multi-data instruction set. The second is an efficient memory subsystem, and the third is efficient execution pipeline with low latency computation modules, and especially we're using mixed clock domains to accelerate it. This figure shows the instruction structure. Each instruction is 64-bit, and each byte represents a configuration for the underlying accelerator. For example, the operation code, the feature size, the kernel size, and so on. We will see more benefits of this instruction set shortly. This is our memory subsystem. There's one thing I'd like to highlight is that we're using a variable length line buffer. I think the line buffer concept is not new for most of our audience, but we are using a variable length line buffer that here the kernel size and the buffer depth are both configurable by instructions. So in this figure, we can see that if we change the kernel size, we can actually turn off a few lines. And if the feature map size changes, we can adjust the buffer depth without computation waste. And the next secret is the mixed clock domains. In the right side, we can see that in the blue box, we are using clock domain 1, but for this adder tree, we are actually using clock domain 2, which is twice as fast as clock domain 1, so that this adder tree can be computed independently with twice clock speed. And here are the details of the key computation units, the Turnerized computation unit working at clock domain 1, and this adder tree working at clock domain 2. So finally, this is the overall evaluation. Comparing our implementation with existing works, we see that if we're targeting the same platform, we are much faster than the previous work. And even when comparing with more powerful platforms, we're not bad. For example, with this BC706, we're achieving comparable FPS. So this TDLE is ultra efficient. So to conclude this talk, we introduced the 3 works. First, the ultra-low memory training that we used rank adaptive tensorized training, and we implemented an FPGA accelerator. And the second is an ultra-low bitwidth quantization called VecQ by proposing vectorized quantization loss. And the third is an ultra-low latency accelerator called TDLA. There are tons of other enabling technologies for edge intelligence, and we're expecting more exciting follow-up works in this area. So this is all of my presentation. Thank you very much for listening. If you have any questions, please feel free to reach out at Shark Lab from Georgia Tech. Thank you very much.